Just think about this for a second. Billions of people around the world face a daily struggle for clean water, something, many of us just have on tap.
It's a stark reality. And the fact that millions die every year from waterborne diseases, it's just devastating. Really highlights the scale of the crisis.
Absolutely. It's huge. But what if we could change how we even think about getting water? Like tapping into the air itself, even in really dry places.
That's exactly the idea we're diving into today.
Exploring this really, quite groundbreaking approach, harvesting water right from the atmosphere.
And there's this fascinating new technology coming out of a collaboration between engineers in Australia and China.
Right.
They've basically developed a kind of sponge, a special sponge powered by sunlight that literally pulls moisture out of the air.
The sunlight-powered sponge.
Okay. Yeah, our sources, they detail how researchers from RMIT University in Melbourne and Zhejiang A&F University in China, they've been working on this. It could be a really game-changing, low-cost way to harvest water.
Yeah, let's try and unpack this. It sounds almost like science fiction, pulling water from, thin air.
Uh-huh.
The basic idea, as I get it, is capturing humidity, the moisture that's just naturally in the air, and then using solar energy, sunlight, to kind of squeeze it out. Is that roughly it?
That's the essence of it, yeah. Precisely. And, it's worth comparing this to other methods.
Like fog harvesting.
Exactly. Fog harvesting works, but obviously you need fog. And then there's radiant cooling, which needs clear nights and big temperature drops to get condensation.
Right. Limitation.
Big limitations. What makes this solar wood sponge so interesting, according to the research, is that it works across a much wider range of conditions.
Wider range? How wide?
We're talking relative humidity from 30%, which is pretty dry, all the way up to 90%.
Wow. Okay.
And temperature-wise, from a chilly 5 degrees Celsius up to a pretty warm 55 Celsius.
That kind of flexibility. That does sound like a potential breakthrough.
It really could be.
So this solar wood sponge, let's get into the material itself. It sounds intriguing. The sources mention refined balsa wood.
That's right, balsa wood.
We all know balsa wood, right? Super lightweight, porous, model airplanes and stuff. But how do you get that to soak up moisture from the air and then release it on cue with sunlight?
Well, that's where the clever material science comes in. Dr. Howe and his colleagues, they describe it as this carefully designed wood-based composite.
Composite, okay.
So the balsa wood, with its natural porous structure, provides the basic scaffolding,
The framework.
Exactly. But the key is what they've added to it. They've infused it with lithium chloride.
Lithium chloride. I know that's used in dehumidifiers, right? It really attracts water.
Precisely. It's very hygroscopic, meaning it strongly absorbs moisture. But they didn't stop there. They've also added iron oxide nanoparticles and a layer of carbon nanotubes.
Nanoparticles and nanotubes. Why?
Well, those seem to enhance the process, possibly improving durability and maybe how efficiently it absorbs and releases the water, especially the lithium chloride part. It's like a team effort at the material level.
A synergistic mix, it sounds like.
That's a good way to put it.
And it's not just the sponge material on its own. The actual device has a whole setup. I read it fits inside a cup. There's a dome lid, some kind of anti-pollution tray, a cooling system, and it's all solar activated.
That's right. It's a complete little system. They've thought about the whole process.
So capturing the vapor, but also making sure the water collected is clean and easy to get out?
Exactly. The dome lid probably helps trap the water vapor once it's released by the sun.
Right.
And that anti-pollution tray is crucial, right? It shows they're aiming for drinkable water.
Potable water. Yeah, that's key. Okay, performance. That's the bottom line, isn't it? How well does it actually work? In the lab, under, let's say, high humidity, 90%. The sources say it absorbed about 2 milliliters of water for every gram of sponge material.
Which sounds quite good, doesn't it?
It does. But what's really interesting is that it apparently released almost all that water, nearly 100%, within about 10 hours, just sitting in the sun.
And the report suggests that's better performance than most other methods currently being explored. And potentially cheaper, too.
Cheaper is always good.
Definitely. And the efficiency really stands out. They did this test with 9 little cubes of the sponge, each one less than a gram.
Tiny.
Yeah, tiny. And together, those 9 cubes absorbed and then released 15 milliliters of water. That gives you a real sense of the capacity.
15 milliliters.
Yeah.
Okay, but lab conditions are one thing. What about outside? Real world?
Good question. They did test it outdoors.
And?
The results look promising. They captured about 2.5 milliliters of water per gram overnight. and calculated a daily water collection efficiency of around 94%.
94% efficiency. That's really high.
It is. Very efficient conversion of the captured moisture.
But what about those drier places we mentioned? The 30% humidity scenario.
Even then, it still worked. It absorbed about 0.6 milliliters per gram at that lower humidity.
Still a usable amount.
Absolutely. And that's perhaps the most significant part. Its potential in arid or semi-arid regions where water is scarcest and other methods might just, well, not work well enough.
That really broadens the potential impact.
It does. And interestingly, they actually used artificial intelligence in this research
Aye.
to help predict and optimize how the device would perform, the water harvesting, the release under all these different conditions, temperature changes, humidity fluctuations.
So using AI to fine-tune the design and predict real-world results.
Exactly. A very modern, data-driven approach to developing the material and the system.
You know, something that really strikes me is using wood. Just basic wood as the foundation.
It's quite elegant, isn't it?
Yeah, it feels grounded.
Yeah.
The sources say this helps keep costs down, obviously, but also gives it structure, and the natural pores in the wood actually help move the water around inside.
Right. It's leveraging nature's own design.
It's this blend, isn't it? Nature-inspired structure combined with these high-tech modifications, the lithium chloride, the nanoparticles.
That blend is often where real innovation happens. And think about sustainability. Using wood, a renewable, biodegradable material. That's a huge plus.
Makes the idea of mass production and deployment, maybe in remote areas, seem much more feasible.
Much more realistic. And they also tested its toughness.
Oh, yeah. How'd it hold up?
Apparently, they stored it at minus 20 degrees Celsius for 20 days. Freezing cold.
Quality.
It kept its flexibility, kept its ability to absorb water. Excellent freeze resistance, they called it. Which is, unexpectedly useful for different climate.
That is useful. You wouldn't want it falling apart after one cold night. What about repeated use? Does it wear out quickly?
They tested that too. 10 cycles in a row, absorbing water, releasing it, absorbing, releasing.
And the performance?
Stayed pretty stable. Less than a 12% drop in efficiency over those 10 cycles.
Okay, so reasonably durable for practical use.
Suggests it could last a decent amount of time, which is vital if you're relying on it daily.
So applications.
Yeah.
Where could this really make a difference? I mean, emergencies, natural disasters.
Yeah.
That seems obvious.
Definitely. Imagine after an earthquake or a flood, water supplies are contaminated or cut off. A portable unit like this, just needing sunlight, could be life-saving.
Providing clean drinking water on the spot.
Exactly. But it's not just for disasters. Think about remote communities, places without reliable pipes or wells.
Off-grid water.
Precisely. And because the sources say these units are scalable, you can make bigger ones or link lots of small ones together.
Like an array.
Yeah, an array. It opens up possibilities for community-level water supply in areas that are really hard to serve otherwise. And relying only on the sun, that's huge for sustainability and running costs.
No fuel needed, no complex power grid.
Yep.
And the cost factor seems key here. You mentioned balsa wood is cheap, widely available.
Right, and the manufacturing process itself isn't described as being incredibly complex. That combination points toward affordability, potential for mass production.
So it's not just a cool lab experiment. It could actually be a practical solution for water scarcity on a large scale.
That seems to be the hope and the direction they're heading.
Are they? Are they talking to companies? Trying to get this out there.
Yes, according to the sources, they're already in discussions with potential industry partners.
For what? Pilot projects.
Pilot scale production, field deployment.
Okay.
Basically taking it from the lab into the real world. They're thinking about integrating it into modular water from air systems.
Modular systems. Okay, that makes sense for scaling up.
It does.
What about improvements? Can it get even better?
Well, they're exploring ideas. Like, what if you combined this with solar panels for electricity and maybe some kind of thermal storage?
So you could potentially run it 2047. Even when the sun isn't shining.
That's the idea. Overcoming the limitation of needing direct sunlight for the water release. That could significantly boost the daily water output.
And more tech. More AI.
Potentially. They've talked about using IoT sensors, Internet of Things, to monitor the environment, humidity, temperature, sun.
And automatically adjust the harvesting cycle for peak efficiency.
Exactly. Smart, automated systems. And even using more advanced AI to design even better materials. Screening thousands of potential combinations computationally.
Predicting long-term performance. How? So the technology itself could keep evolving quite rapidly.
It seems like a very active area of research with lots of potential pathways forward.
It's also worth mentioning the people and institutions involved. It gives it weight, doesn't it?
Absolutely.
The senior researchers mentioned are Dr. Derek Howe from RMIT in Melbourne.
And Dr. Yunfeng Hao from Zhejiang A&F University in China.
And there's a collaboration between RMIT and 5 other Chinese research institutions.
That kind of international teamwork is often essential for tackling these big global problems like water scarcity.
For sure. And for anyone listening who really wants to get into the weeds, the scientific paper is published.
Right, it's available.
It's called, let me get this right, Development and Characterization of Novel Wood-Based Composite Materials for Solar-Powered Atmospheric Water Harvesting, a Machine Intelligence-Supported Approach.
Quite a title.
It is. Published in the Journal of Cleaner Production back on February 28, 2025.
Okay.
We had the DOI, if you want to look it up, 10.1 Euro 1 J.J.Club.2025.145061. And it was funded by the National Natural Science Foundation of China.
Good to know the source and the backing. It lets people, dig deeper if they're interested in the real technical details.
Exactly. So, wrapping this up,
Yeah.
it really feels like this innovation could be profoundly significant. Tackling global water scarcity, especially for off-grid use for disaster relief.
Yeah.
It offers some real hope.
It really does. And for me, the sort of aha moment is using something so, simple in concept-modified wood for such a massive, complex problem.
Yeah, that blend again. Nature providing the blueprint, enhanced by some very clever, cutting-edge tech.
It's a beautiful example of that synergy, looking to nature, but using our best tools, like AI, to optimize it.
It really makes you think, doesn't it? This blend of nature and advanced tech, it's powerful.
Which leads to a final thought, maybe for you listening. Just imagine, right? Imagine if this technology can be scaled up effectively, made affordable, deployed widely.
The impact.
How many lives could that change? How many communities could become more resilient, especially with climate change impacting water resources? It really pushes you to consider the bigger picture for, sustainable living and managing our planet's resources better.